this video, we're going to go over the electric side of my lightweight hybrid sports car project. We're in my office right now. This is kind of where the battery lives at the moment. Not a lot of space in the spare bedroom where the mock-up is to work on this stuff, so until I get the right size tube to put this in the mock-up, I'm just working on it in here. So let me give you a little introduction to the project if you didn't see the first video. I'm building a lightweight hybrid sports car with almost zero hard tooling, at least I'm trying to. It uses a small, powerful motorcycle engine. So currently it's BMW K1600, which is a 1.6 liter straight six, makes 160 horsepower. Hybrid system offers about another 40 horsepower peak. There's other good motorcycle engines to use, that's just what I'm using right now. So the key to this whole project, the reason why this hybrid system works, which I'll go into, is that the power requirements for a light vehicle are low. When you go into higher power, you need higher voltage, but if you can stay under 100 volts, this whole system works very nicely, and because of what it is, this whole system works. So sitting in front of me right now is the traction battery. Some headline details, I covered them in the other video, but I'll go over them again. This is 72 volts nominal, 84 volts charged. It's a 30S1P configuration, so I have no parallel pairs in this pack. It's all series. That's just kind of the nature of lithium titanate. The LTO cells are 2.3, 2.4 volts nominal, so you really want to have a bunch in series. Yeah, I'm wearing gloves. It's not very dangerous right now. These need to be compressed to really get the connections. I could bring the multimeter out to show you that, but just in case, I'm wearing some gloves. So this pack can do 500 amps out. So at 72 volts, that's around 30 kilowatts. It can do about 400 amps in, actually a little more than that. So about 30 kilowatts of regen in. So that gives you a lot of capability to not only put power down, but get it back into the pack however you want. It's very, very flexible. Another important part about LTOs is that they're rated to about 20,000 cycles. I've been into this in the other video. They're very stable at cold temperatures, and they can be discharged to 0 volts several times safely. So if you need some emergency range, this pack will provide that range to you. The cells are also incredibly safe. You can hammer a nail into these. They smoke a little bit. They don't catch fire. You can shoot at them. Nothing really happens. They just discharge. So if you're an enthusiast and you're skeptical about putting a battery in your car, a lithium battery, which is totally understandable, this is about the safest chemistry you can get. So these particular cells are called skibs. They're made by Toshiba. I'm sorry about the list. Again, if I don't have the list, I'll just talk on forever. These are the 20 amp hour versions. They make a 23 and 26 amp hour version as well. So if I wanted more capacity, I could do that just by going to the different cell. These were available. They were on sale. I looked it back up. The whole pack cost me about $500 for just the cells, not including BMS or bus bars or stuff like that. I could also add more cells if I wanted more voltage. Most of these inverters are rated up to 100 volts. I know Curtis makes one that's 144 or higher. So assuming I have the space to fit it in the tunnel, it doesn't interrupt anything, then yeah, I could go slightly higher voltage to get a little more capacity. That being said, I'm very happy with the capacity now, so I'm going to stick with this pack. I know the problem is that once you get into these higher amounts of cells in series, it's hard to find a BMS that'll support that. I'll go into the whole BMS in a minute, but that's just another key thing. It was hard enough to find this BMS for this pack, so if I wanted to add more cells, it might be tricky. So let me go into the pack construction here. So again, 30S1P. The base of this is these lasered copper bus bars. They're from Senket Send. I'm still working on kind of fixing these, so if you know anything about soldering, you know it's going to be impossible to solder the BMS wires to these really thick copper bus bars. So I'm working on a new version that has a little tapped hole in the middle, has a little M3 screw there. So I'll just be able to tighten those BMS leads down to every bus bar. That'll make my life a lot easier. I'm not sure if I'm going to drill all these and do that. I probably will just for this prototype and then tap them. But in the future, these can just be ordered tapped, which is great. The cells are held in place by a big plastic spacer. Obviously, that can't be metal, or else this thing would just turn into a red hot piece of metal in short order. So these keep the cells the right spacing. This piece also has to be modified to accommodate those new BMS screws. But this is just kind of an intermediary part that I use to prototype this pack. On top of this goes cap nuts. So they're plastic cap nuts right here. I'll do a close-up of these. But that just ensures that the pack is going to be very secure in the tunnel, but if it jumps or anything, if the fixtures come loose, then it won't, these bare terminals won't be impacting aluminum tunnel. That would just not, that would be bad. So the cap nuts ensure that the pack is like extremely isolated inside the tunnel. And then this will have a metal enclosure. I'll switch to CAD and I'll show you a little picture of that. That's going to have to change as well. I'm going to have to add a tray to accommodate the BMS. There's going to have to be some holes in that, all kinds of stuff like that. The initial battery pack design was very preliminary, just to kind of get some measurements so I knew that it would fit in the tunnel. Now it's changing because this stuff is going to go in the tunnel soon. So that all has to be finalized. And the terminals for the battery are right on this end. That's a positive and negative terminal here. So they sit at the front of the tunnel. Terminals come right off. And Bob's your uncle there. So I'm going to have two master solenoids off the battery. So if you don't know, if you're not familiar with electric vehicle battery packs, they have two contactors on the positive and negative sides of the battery. I'm going to have that too. So when you turn the car on, you're going to have to flip those two switches, turn on master power. That's a safety feature. There's two because if one fails, it doesn't get stuck open. Again, all EVs have that. I plan to have that. I have those contactors around you. I'll put up some B-roll of the contactors right now just to show you. They're pretty easy to get your hands on. They're expensive new, but there's used units all over the place out of packs that have been salvaged. So that's what I'll be using. But let me go deeper into the BMS here. So these LTO cells, for reference, I bought them about a year ago. They have been sitting in my garage for months, and they have not gone out of balance at all. They have not discharged almost at all. They've discharged like 0.01 volts a piece, and they're all almost still perfectly balanced. So this is a very stable chemistry. You don't really need a BMS. I know people always say, oh, you need a BMS for everything. It's true with lithium-ion cells. Lithium titanate cells, it's less true. My original plan was to just sort of come up with a way to monitor all the cells' voltages, so if one needed to be balanced, the pack could be removed and balanced easily manually. But the way it's kind of, the whole car has come together, that pack is difficult to remove. So the BMS is there. It's not truly necessary for balancing. These cells stay in balance very nicely. They're brand new cells. But it's mostly for monitoring because the pack is difficult to remove. You know, you're probably going to have to pull the front drive unit to pull the pack out. It's just how the tunnel, my closed-in tunnel system works, unfortunately. And yeah, the big advantage of the BMS are the monitoring and the connectivity. This BMS I'm using, I'll put some B-roll up of it. Just a kind of generic Chinese BMS, but it has some cool features. Again, Bluetooth. It has 4 temperature monitoring probes, so I'll be able to look at the temperature of the pack in 4 different places to really get an idea of how it's performing, what the temperature like, how far you can push it, all that good stuff. I'll get back to the list here. So I looked at active balancers as well. So they make 30S active balancers for LTOs. An active balancer, if you don't know, it's just like it's like a variation of a BMS almost. It's very interesting how they work actually, but for this, they don't make, or I couldn't find ones that had the connectivity that I liked, because this is going to communicate with Bluetooth with an onboard Android computer, so I can monitor all that in the vehicle. And I just didn't see a active balancer that had those features. So for other LTO projects, active balancers are very good, especially just sort of using them when the vehicle is being charged up that last little percent. But they're not quite right for this project yet. If there was a good Bluetooth-enabled active balancer, I'd probably use it. And yeah, again, the bus bars have to be modified to accommodate all 30 leads and the 4 temperature leads. And there's some kind of contactor feature on there as well, which I may or may not use. I might just short that. But yeah, this BMS is rated, I think, for about 350 amp continuous, 450 amp continuous, but a 900 amp burst. So it's plenty for my needs. If I break it, I'll just get a new. It was pretty cheap. It was about $120. In the future, I'd really like to do all that stuff myself. It seems like kind of a tall order, but again, having all that stuff integrated, and I know how to make PCBs and getting all that stuff right seems relatively straightforward. Not the programming side, not finding the right chip, not all the kind of passives, but the actual design itself for a BMS board is pretty straightforward. And I would like to be able to integrate that. So let me talk about the motor. Again, I'll put up some B-roll of the motor right now. Again, I mentioned in my first video, it's about 15 pounds, 25 to 30 kilowatts peak power, so about 30 to 40 kilowatt or horsepower. It's about 20 horsepower continuous. That's like all day long. So all motors have kind of burst and like regular going features, stuff that can dissipate the heat forever. It kind of depends on how well you cool the motor, where it is in the car, that kind of stuff. But I think I'll be able to achieve those 30 kilowatt peaks on a pretty regular basis. There'll be a big radiator fan in front of the motor. The motor is actually right behind the front grille, so I'll have very good cooling, and I think I'll be able to take advantage of that, those peaks very often. The motor can handle a 350 amp burst, and it's 27 kV. So if you don't know what kV is, it's very simple. kV is just RPM per volt. So this is very important for a setup like this. So if you put 1 volt, a 1 volt, whatever sine wave into the motor that I'm using, you would get 27 RPM, 10 volts, 270, etc., etc. It's very important. You have to match the kV of your motor to the voltage of your battery and to your wheel diameter and your transmission ratio. And transmission ratio in my case is just the differential. When you do that, you get the efficient range of this motor within a certain speed. So, for instance, this is 27 kV, 84 volts peak, 72 nominal. This thing goes efficiently, naturally, up to about 40 miles per hour. So I'm very happy with that. I could always change the motor if I wanted more speed. I'm getting a lot of low-end torque as a result of using a low kV motor. So, as I understand it, lower kV motors produce more torque at lower RPMs with less current. Ideal for this kind of application. If it's not quite right, I can always alter the differential ratio. There's a couple available in the Audi diff I'm using, or go to a different kV. The VESC controllers that I'm going to use, and I'll go into the controllers next, they have field weakening or flux weakening, so they can actually go beyond that natural kind of max speed of the motor. It's less efficient, you have less torque, but if you want more speed out of this thing, you can absolutely get it. It's just a setting in the inverter. So let me go into the inverters that I'm going to use or plan to use right now. So again, this is kind of like a tricky subject if you go for high voltage. They're all very kind of business to business, professional engineers using them, like almost exclusively CAN communication. The connectivity isn't very good. The hobbyist stuff is getting better and better though. My first choice for the inverter is the Trampa VESC. It's called the STR500. Trampa is a reputable company. They make great stuff. It can allegedly do 500 amps continuous. So that's plenty for my application. It's an ideal choice. They have some cool features in there. They actually have some DC-DC converters on it, which I might use, might not. But again, good connectivity. I can connect to it with Bluetooth from the onboard Android computer, monitor all kinds of stuff, adjust settings on the fly. The other option, so I will say that is, I think it's currently out of stock, so I need to pick one up when it comes into stock. They're about $1,000, which is expensive for this kind of thing, but it's a small price to pay for getting a reputable inverter. It's made in the UK, it's a good unit. The other option is the Flipsky 75450. So I have used Flipsky stuff. There's actually a Flipsky inverter hooked up to the mock-up right now, or controller rather, just as to get the motor spinning. I've used Flipsky stuff in the past. It's kind of hit or miss. I've smoked one of their inverters before. I don't know how it happened. Seems like it doesn't have a lot of protections. Again, does it need protections? I don't know. Maybe I was just being an amateur with it. But I don't want to use the inexpensive Chinese stuff on this prototype if I can avoid it. I would like to use the final stuff. The Trampa board seems really good. So I'm going to end up going with that if I can get one. This motor, the sensor wise, I'm using Hall sensors right now. That's what the motor came with. Encoders seem interesting. I think it would be pretty easy to apply an encoder to the motor I have. Might do that in the future for better low speed control, but for now I'm just going with Hall sensors. And for anyone who's curious, you do need a pre-charge circuit for this, a pre-charge resistor. Flipkey doesn't mention that anywhere. Should set off an alarm bell, but Trampa in their user manual say, yeah, you want a pre-charge resistor, so you're gonna have to make that circuit. It's a very simple circuit, but gonna have to have one. Just kind of letting you know that I'm aware of that. I will say that I'm also looking for other 100 volt inverters. If anyone knows of any good, reputable, relatively high voltage inverters like this, please drop a line. Very happy to look at them. Very happy to consider them. As long as they're Bluetooth enabled, that's fine by me. That's really my big concern there. And one idea I want to mention that is more aesthetic on this project than anything, but I don't want anybody to kind of snatch this idea before I'm done, is that one of the cool parts of this is the inverter. I might need to add auxiliary cooling. The inverter is cooled by a heatsink that's exposed on the hood. It looks kind of like, an old Challenger or Charger shaker hood. So I just thought that was a cool thing to add. And I don't know if that cooling will be adequate. I might need to make it bigger or add more surface area. But that's going to be kind of like a water looped in heatsink. I just thought that was a neat idea. Maybe I'll change that. I think it would be cool if I ever made more high performance models where that heatsink kind of grows or there's more of them. Just so you can really see that electric power. And when you're stopped, if you just went on a big run, you're just able to see that heat rising off the heatsink. I think there's not enough interaction with the electric power in hybrid cars, especially in hybrid sports cars. You don't see it, you don't experience it, you don't feel it, you don't interact with it certainly. So that's just one of those little cool things that I wanted to kind of call back the electric power with. That's going to be an expensive thing to mill, but I think it's really important. So I touched on the interaction a second ago. Another good reason to use VESC controllers, I'm sure that other higher end inverters with kind of CAN connectivity, VESCs have CAN, but I'm going to use it. I'm not familiar with CAN. I've been told it's pretty easy, but these VESC controllers, there's an Arduino library where you can hook up an Arduino and alter the settings of the VESC within the Arduino software. So that's how the connectivity or the interaction is really enabled. So the power in, power out, static regen will be adjustable with sliders. I plan to try that pretty soon with these slide pots. If you've ever been like an old E30 or something like that, the climate control is all slide pots. I just like that. I like the interaction. I'm not going to use these knobs. These knobs are pretty hideous. I'm going to get my own knobs done. But that's how that interaction will work. It'll be all, you want more power, you slide it over. You want less, you slide it back. All kinds of stuff like that. I think it's just a cool solution to that. Why make them vertical? Again, making that interaction possible and then making it a cool experience is very important to me. One thing on that front is that, so when I was talking to the E-Ray people, what they mentioned was, in certain conditions, the rotor regen can be so powerful that it can actually lock up the front wheels, the front tires. So that's one of the reasons why my front diff is open, so that if you do get traction limitation, you will have one tire spinning. That being said, I think there's ways to kind of challenge that or adjust that. I think there's a traction control feature inside VESCs. I'm not sure how that works. I've never used that. I've just made go-karts with it. It's a small problem to solve, or it could be a big problem. I'm not sure yet. But again, it's something that I have to figure out once the prototype starts driving. So again, the driver will be able to, if it's rainy, you get a little lockup, turn down the regen, turn off the regen, ultimately up to the driver. So an important part about this is how the power is applied by the driver. So that is something, again, that's going to have to be tested. I would like to have, if you've ever driven a new GM EV, a higher end one, the regen is on a fully variable paddle, like in a Lyric, for instance, where independent of the mechanical brakes, if you want full regen, you yank the paddle on the steering wheel and it gives you full regen. And everything in between, so it's a full gradient. So you can pull it halfway, you get half the regen, and again, everything in between. I think something like that would be useful. I know how to apply that. If there was something like that on the power on too, maybe on the opposite side of the wheel, that's a possibility. A button on the steering wheel to apply a fixed amount of power is also a possibility. And a kind of wide open throttle button under the pedal is another thing I'm looking at. So if you want to command all that power without pulling a pedal or a paddle, you can just floor it and you'll get max power. These will all be settings that the driver can adjust. So if they want to apply the power one way or two ways or multiple ways, all of those can be engaged. I might play around to figure out the best one of those options to try and figure out, are these redundant in any way? But that's how that's going to work. So another really important part of this is enabling that connectivity in other ways. So, for instance, the BMS has Bluetooth, the VESC tool has an onboard shunt, or the VESC controllers have an onboard shunt. I'm not in love with the VESC interface. I think it's useful for adjusting settings or checking things. Same with the BMS interface. It's very basic. I do like Victron stuff a lot. So the Victron Smart Shunt and their Servo GX system seems like a really good solution for this, especially for the main gauge. So that can display output power, state of charge for multiple batteries. So I can have a smart shunt on the high voltage and on the low voltage. So I'm powering accessories. I notice the low voltage is going down, state of charge is going down. I can monitor that. I can turn on the DC-DC converter between the traction and the 12 volt, turn off the accessories maybe, but I'll be able to monitor both those things. And they have a really slick looking display to do it. It looks very OEM. So that just seems like a very well sorted, it's a very accurate smart shunt. That also has onboard temperature sensors, so you can monitor, again, the BMS has temperature sensors, which I'm going to output, but if I wanted to measure just like an average pack temperature, maybe in the middle, or the cooling water temperature for the inverter, I can measure both those things and just see them right on that display. Another really cool thing about the Servo GX, which this is not an electric power thing, but it's kind of a vehicle package thing, is that they have wireless ultrasonic liquid level sensors you can connect to it. So for the fuel tank, I can get whatever fuel tank I want. It doesn't have to have a sender in it. I don't have to put a sender in there. And I can just have the liquid level sensor at the bottom of the tank sending to that Servo GX directly. So you basically instantly get a really slick looking gauge package in that display. RPM is another situation, but again, if I have to have a separate tack on that for the prototype, that's just going to have to be the way it is. And finally, I've talked about the onboard Android computer in this thing. So that is a Cadas Edge 2, it's a single board computer. That's going to be managing all these systems kind of. Everything connects via Bluetooth. There's going to be a VESC tool on there. It's going to be the BMS software. But since it's Android, it's going to have Google Play, YouTube Music, Google Maps, all that kind of stuff. I'm using a kind of long, narrow display for it. I just think it looks very interesting. I'm interested to see interactions. I've tried a lot of apps on it and they'll look pretty cool. I think it would be interesting to integrate. So I think I'm going to end up using that. That will also be controlling the audio system. So I'm just going to have 2 speakers in this thing for like music. This is not that kind of car to have like a 10 speaker sound system. In the future, maybe I'll add some more, but I think 2 nice speakers is right and left channel is plenty for now. So that's a pretty powerful little computer. I'm gonna have to make a case for it so that water doesn't get in, all kinds of stuff like that. But that'll be under the dash somewhere, powering all that kind of cool stuff, and maybe doing some other interactions too. But so that stuff will all be sorted out into the interior. All these interactions, these switches, slide pods, all that kind of stuff still have to be integrated. I have an idea of how it's going to look, but I have to get into the details of how that stuff is actually going to be mounted, and again into the bracket phase where you're just designing a million brackets to mount all this stuff. I think the interior is going to be really cool. I'm looking forward to doing it. It's actually probably going to be one of my favorite parts. There's other features of that I haven't shared yet that are going to be cool to go into, but yeah. And again, I'm very open to comments and suggestions on this. If someone has a better solution for monitoring BMS, like better than the Victron stuff, it would be hard to believe. As a side note, Victron should make a traction inverter. If they made one, I'd buy it instantly. Any comments and suggestions on that front? For anything really. I'm, not an amateur at this stuff. I'm pretty good at it, but there's a lot of people that know a lot more about it than me. So if you have any ideas or anything, please drop them in the comments. I will happily, I see all the comments. I'll respond to the comments that I think should be responded to. So this is a very, difficult process for me. It's a long project, but any help I can get would be greatly appreciated. So next time I'll go into different stuff. I think, I'm working on the ergonomics a lot right now. That's a very tricky subject in a car with a tight interior like mine. But it's a very interesting problem to solve. I've already kind of adjusted the cad of the main chassis to get a little more space in there. So that's an interesting topic. Going to the mechanical side of it, the engine itself, little stuff like that, drivetrain, brakes, all that kind of stuff I'll talk about as well. But yeah, that's it for now, and I'll see you guys in the next video.